Okay, welcome back. So this is just going to be a shorter video. I thought I could get it in the first 15 minutes here, but I'm getting better at it. In any case, we just got done talking about classifying waves by shape. Really, transverse waves are up and down vibrations, which cause energy to move in a certain direction. It's actually perpendicular to the direction of the vibration or the disturbance. So the second way of, or the second type of wave is called a longitudinal wave. Longitude, you can think about it lengthwise. So the particle is going to be moved back and forth, and the energy is going to move in the same direction. So the slinky, I'm not sure if you can see this video or not, like I said, but basically you can see a pulse of energy pushing through, right? Remember, that actual slinky itself moved back and forth. It's not the one that's traveling. It's the energy traveling through it, even though it's moving along it. So yeah, these are the basic two types. We typically, when we look at longitudinal waves to understand what they look like and what they do, we look at them in terms of how much compression they have and how much rarefaction. Compression, you should probably already know, is when it's being pushed together. Rarefaction is just another fancy word for being pulled apart. So this might look weird, but if you think about how the slinky, it gets pushed together, it almost creates like this little compression zone that travels through. And if there's a place that's pushed together more, there must be a place that's being pulled apart more, which is that rarefaction area. So once again, longitudinal waves have compression and rarefaction, and we'll dig into that a little bit more in the next lesson. So besides the classifying them by what shape the disturbance takes, you can also classify them or sort them by whether they need something to move through or not. So I want you to pause for a second and think, what kind of waves do you know of and which ones would need something to go through? Okay, if you're coming back into the video now, basically, waves that need a medium to travel through, we call them mechanical. I know we've already started to use that word mechanical for about a million things, and I'm sorry, it's just the term for it. So mechanical meaning that it's actually stuff touching other stuff. You have air molecules touching other air molecules in a sound wave. You have water molecules touching water molecules in a water wave. Ropes, it's the same idea. Earthquakes are waves that pass through the earth. There's a whole bunch of different shapes they could take, but this is simply saying certain types of waves need to move through a medium, and we call those mechanical waves. There's really only one type of wave that doesn't need to travel through a medium. Actually, probably two now. Now that they discovered gravitational waves, and that would be electromagnetic waves. So electromagnetic waves don't need to travel through something to travel. You think about the light from sun as being an electromagnetic wave. It travels very quickly, and it travels through literally nothing at all. Interesting enough, light will actually slow down when it travels through a medium. So it can travel through something, but it likes to travel through nothing. It doesn't like have preferences like, I don't want to travel through this. It will travel faster through nothing at all. And that's only electromagnetic waves. So it might be weird to think about this. Examples of these is like, it's not like X-rays and radio waves and infrared and microwaves and visible light are all different types of waves. It's all the same thing, but those are all examples of what an electromagnetic wave is. They're the same looking thing. It's just, it doesn't need to go through a medium. Just a brief snapshot about what electromagnetic waves are, because we're going to dig into this a lot more when we start talking about light. These are waves that are produced by electromagnetic fields. So it's actually two fields at the same time. We'll see it in a second. And they are transverse waves. So if I were to say now, hey, sound is a mechanical longitudinal wave, you should already be able to tell that it's a wave that is mechanical, so it has to go through something, and it's longitudinal, meaning it's a pushing together and a pulling apart, and it travels in the same direction as that vibration. kind of like the second slinky. Now light, if I'm trying to explain to you what light is in terms of a wave, it's an electromagnetic transverse wave. So it means it travels through nothing. It doesn't have to travel through something to go. It actually carries its own particle. We call it a photon. And it's transverse, meaning the force that's creating that vibration is in perpendicular. It's not along the same line. It's actually 90 degrees to the motion of the particle, or the wave in that case. So electromagnetic waves can be all of light. It could be gamma rays, X-rays, ultraviolet, the stuff we see called visible light, infrared, microwaves, and radio waves. But it does gets caused by electromagnetic vibrations. It's really confusing. Just to give you an idea, so this is a GIF trying to represent how light works. You have an electromagnetic field, meaning the E here. This is like an E with an arrow on top to represent a field. Basically, you can see that it's it's going up and down, just like a pendulum would. If you were to graph a pendulum, on Friday we did that with a couple students, it would look kind of like this. So this is how light works. It has an electric field this way, and at the same exact time it has a magnetic field going 90 degrees to whatever it is. So if electric is down, magnetic's that way. If electric's up, magnetic's that way. I'm not going to get into how those things create forces or what's going on in there. Just at this point, just say light is very weird, and it's an electromagnetic field that causes the energy to push the light energy along. Even light energy itself is not just a particle, and it's not just a wave. It's kind of like both at the same time. If you want to know where the particle is, you could tell that a duck would be moving up and down in the water, right? But like I said, light does not need to travel through anything, so you're not actually pushing on anything, and the energy itself could be anywhere in here. It's just kind of weird. So it does travel in a straight line-ish, but it's not like it's in any one point. That's why we say it doesn't need to go through something. It's an electromagnetic wave for that reason, and it is transverse in how we represent it. Usually we represent it this way, which is up and down. Okay, that's the end of Waves Lesson 1. I know it's kind of confusing. We're going to dig into it a little bit more. The next lesson will be about properties of waves. So don't forget to take a look at the other video I posted just from YouTube, just in case you're really lost at this point. Ask me some questions, email me, or come out to the Google Meets, and make sure to do Google form to get the grade for this assignment. Take care.